Okay. I left off, I was going through the reference manual to see if there's anything that really sticks out that would be really interesting to read up about. Maybe at some point in the future I might go through the C reference manual, but I'm not going through this one. This one's like very old. Okay, so we talked a little bit about storage classes. So let's get back to there. And then I don't think anything here was interesting. Type qualifiers, I guess. Objects and L values. Conversions, integral promotion, integral conversions, integer and floating. Floating types, arithmetic conversions. Pointers and integers, void. Pointers to void. Expressions. Postfix incrementation, unary operators, prefix incrementation operators, address operators. Address operator, it's not plural. The indirection operator, I always call it the dereference operator. One's complement operator. Logical negation operator. Size of operator. Casts. These are just a bunch of operators. Const expression, comma operator. Declarations, storage class specifiers. Here we go. This might be interesting. Auto, register, static, extern, type def. We already know about all these. Type equivalents. Two type specifiers Two type specifier lists are equivalent if they contain the same set of type specifiers, taking into account that some specifiers can be implemented by others. For example, long alone implies long int. Okay. Okay. The external stuff I might want to read. Scope and linkage, pre-processing. A lot on the preprocessor. And then we get into the grammar, which is like multiple pages, and that's it. All right, maybe read a little bit about external declarations. The unit of input provided to the C compiler is called a translation unit. It consists of a sequence of external declarations, which are either declarations or function definitions. The scope of external declarations persists to the end of the translation unit in which they are declared. This is a bit too legalese for me. Here we go, something that might be interesting. Within a translation unit, all declarations of the same object or function identifier with internal linkage for the same thing. An object or function is unique to that translation unit. All declarations for the same object or function identifier with external linkage refer to the same thing. And the object or function is shared by the entire program. Okay. All right, I don't think I need to get into this. It's a little bit too legalese for me. Maybe I'll come back to it at a later time. I do have those extras at the end. I think maybe I'll put those on hold too. I'm not too excited to implement more allocation stuff. I'm glad I spent the time today to kind of grapple with the code that they provide. It's not a lot of code, but it's just kind of like some weird code in that it's a little bit what's the word, obfuscated. Like the actual functionality is a bit obfuscated, because I'm not used to reading code like that where you have these 1 to 2 character pointer names and you're doing all this stuff like, you know, taking a pointer from over here and a pointer over there, then also going through a union because you want the alignment. It's like we can make a better, like more documented, easier to read solution to that problem. But I guess maybe they were also kind of wanting to constrain it to the format of the book as well. So I'm going to put this book on the stack of books that I have read. Completed reading. Bam. So where does that leave us? We could do some work on ePOL file server tonight. Could do some work on, well, there's a whole list of projects that I have. looking over at this stack of books that I have in my queue, and I put SRE books up at the top because I feel like if I am to get a job in the next like 6 months, it's probably going to be related to some type of reliability stuff. Just because I've done so much work in that space. I have the experience. So reading the reliability books, having those under my belt would definitely give me more confidence in those type of contexts. And then of course cracking the coding interview and its sequel would be nice to get done just to do interview prep. So I put those at the top of the list because I think I'm going to be interviewing in the next 6 months or so for a job related to that. But what do I want to do? I want to do the fun stuff. BPF, diving into assembly, Linux binary analysis, CUDA, the massively parallel programming stuff. Like these are the books that interest me right now. The cracking the coding interview and the site reliability book, like that's not where my mind is at right now. I know I probably want to start interviewing in the next like 6 months, but I feel like I want to have some more fun. So I did have the computer systems book up at the top of my list. I'm thinking more now that BPF performance tools or systems performance might be more appropriate for me to stay motivated. Because these SRE books, I could read those like just like as bedtime reading. I don't need to like dedicate 12 hours a day to reading one of those books. Okay, so these are the two books I'm looking at. We got, can't really see it on the camera there, but BPF Performance Tools. BPF Performance Tool by Brenda Gregg. And then Systems Performance V2, second edition. This one's meant for Linux. I don't know which one I want to take on first. So BPF Performance Tools System. I do want to read both of these at some point. And the thing I like about these books is that they're thick, but it's because the pages are thick. Like this is only if I go to the very end, skipping the appendices, like the actual printed text of this book is 740 pages. And it's that thick because it's got thick pages. And the pages are like that paper that's like, it's got a texture to it. It smells good. It has a texture to it that it just screams out like right on me. It's paperback, so the binding can break a little bit as you're reading, which is nice. Anyways, Linux system and application observability. Okay, I'll just read the back of this book. So this was the second edition was updated for Linux. I actually already have read a good chunk of this. Years and years ago, but it was for Solaris Illumos. That's how much I wanted to read it. So I was willing to not be able to run the stuff because I don't run Illumos. But yeah, I gave up on it at some point. It was just a lot. All right, BPF. Use BPF tools to optimize performance, fix problems, and see inside running systems. BPF-based performance tools give you unprecedented visibility into systems and applications so you can optimize performance, troubleshoot code, strengthen security, and reduce costs. BPF performance tools, Linux system, and application observability is the definitive guide to using these tools for observability. The other problem is I don't think there's a PDF available for this, unfortunately. Oops. Can I just quit out of that? Close without saving. Thank you. I doubt there's a PDF for this online. Hey, there it is. Of course there is. Okay, download it. And again, I own this book. I'm just pulling up a digital copy. But I own the book. See, I own it. And I encourage anyone who would ever watch these streams for whatever reason, I wouldn't know why, to actually buy the book if you're going to read it. I used to own this one, but I've lost that one. This one looks interesting. There's a couple books by Rob Pike and Brian Kerningham. I think there's 2. I've heard of this one, and of course Design Patterns, but I have no interest in reading that. All right, let's go back to the is the back cover? Nope. Can I go home? Okay, they don't have the back cover anyways, but I'll leave it up here. Pioneering BPF expert Brendan Gregg presents more than 150 ready-to-use analysis and debugging tools, expert guidance on applying them, and step-by-step tutorials on developing your own. You'll learn how to analyze CPUs, memory, disks, file systems, networking, languages, applications, containers, hypervisors, security, and the kernel. Gregg guides you from basic to advanced tools, helping you generate deeper, more useful technical insights from improving virtually any Linux system or application. Learn essential tracing concepts and both core BPF front ends, BCC and BPF trace. So I have somewhat of a familiarity with those already. Master 150 plus powerful BPF tools, including dozens created just for this book and available for download. Discover practical strategies, tips, and tricks for more effective analysis. Practical strategies, tips, tricks. Okay. Analyze compiled, JIT compiled, and interpreted code in multiple languages. That's what I'm interested in. C, Java, Bash Shell, and more. I would prefer Python than Java, but we'll see what he gets into. Generate metrics, stack traces, and custom latency histograms. Use complementary tools when they offer quick, easy wins. Explore advanced tools built on BPF, PCP, and Grafana. For remote monitoring, BPF Explorer and kubectl Trace for tracing Kubernetes. Wow, I can't believe kubectl Trace got into this book. I had an opportunity to, I think I have a commit on that. I had an opportunity to work on it when it was originally released. Kubectl, oops. Yeah, I got into IOVisor, yep. Who's the gentleman that worked on this? I forget. I think it was this guy? No. Yeah, Lorenzo. He's a cool dude. Yeah, he was at Falco. BPF performance tools will be an indispensable resource for all administrators, developers, support staff, and other IT professionals working in any recent Linux distribution in any enterprise or cloud environment. Brendan Gregg, Netflix senior performance engineer, is a major contributor to BPF, eBPF. who has helped develop and maintain both BPF front ends, pioneered BPF's use for observability, and created dozens of BPF performance analysis tools. His books include bestseller Systems Performance Enterprise in the Cloud. So that's like, okay, just using BCC, BPF Trace, how to use those tools for practical applications. Systems Performance. This is a book more focused on performance. This is more focused on like understanding your systems. Let's read the back of this book. And this is called Systems Performance Enterprise. And I own 2 copies of this book, the first and second edition. PDF. So that'd be this one. Download. So this one's in color. It's nice. Oop. Okay. Let's read a little bit about this book. Systems Performance second edition covers concepts, strategies, tools, and tuning for operating systems and applications using Linux-based operating systems as a primary example. Deep understanding of these tools and techniques is critical for developers today. Implementing the strategies described in this thoroughly revised and updated edition can lead to a better end user experience and lower costs, especially for cloud computing environments that charge by the OS instance. Systems Performance expert and best-selling author Brendan Gregg summarizes relevant operating systems hardware and application theory to quickly get professionals up to speed, even if they'd never analyzed performance before. Greg then provides in-depth explanations of the latest tools and techniques, including extended BPF, and shows how to get the most out of cloud, web, and large-scale enterprise systems. Key topics include hardware, kernel, and application internals, and how they perform, methodologies for rapid performance analysis of complex systems, optimizing CPU, memory, file system, disk, and network usage, sophisticated profiling and tracing with perf, ftrace, and BPF, BCC, and BPF trace, performance changes associated with cloud computing hypervisors, benchmarking more efficiently, featuring up-to-date coverage of Linux operating systems and environments. Systems Performance second edition also addresses issues that apply to any computer system. The book will be a go-to reference for many years to come and, like the first edition, require reading at leading tech companies. Brendan Gregg is an industry expert in computing, performance, and cloud computing. He is a senior performance architect at Netflix, blah, blah, blah. I don't need to read about Brendan Gregg again. He's a cool guy, but I already read about his little bio there. Okay, so now we're at Appendix A. Means a page count on this thing. These are references. All right, this will be 800 pages roughly. So we got 800 pages on that. This one's a little bit sturdier of a printing. These pages feel more like newspapery. They're thick, they have a texture. These are more, it's like a fancier paper. So this is about 800 pages, and this one is about it's about 800 pages too, but it's bigger. Now, both of these books, I feel like I would be really motivated to read. The first book I've already read a good section of it. Maybe, I would say like a tenth maybe. I think I would learn a lot from this book. I learned a lot from both books. This one's more very pragmatic, I would say. In that it goes into things like setting up Grafana and collecting data. It's more a practical applications of tools type thing, I feel like. Whereas this one's more like theory and foundational knowledge for debugging performance issues specifically. So I think I'm leaning towards the BPF performance tools instead of systems performance. While this is much more well known as a book, and I definitely feel like I get a lot out of it. I don't know. Maybe I need to think about this some more, to be honest. So I read the blurbs. Let's look at the indices. See what topics are being covered here. So the contents at a glance. We got methodologies, operating systems, observability tools. There is a section on tools, applications, CPU, memory, file systems, disk, networking, cloud computing, benchmarking, perf, ftrace, BPF, case studies. The use method, SAR summary, BPF trace one-liners, solutions to selected exercises, systems performance, who's who. BPF performance tools. Oh, there's no at a glance on this one, is there? Oh yeah, there's an at a glance here. All right, so we got introduction, technology background, performance analysis, BCC, BPF trace, using BPF tools, CPU, memory, file system, disk I/O, networking, security, languages, applications, kernel, container, hypervisors. This seems very structurally very similar. Additional topics, other BPF performance tools, tips and tricks, common problems, appendices, BPF trace one-liners, cheat sheet, BCC tool development, CBPF, BPF instructions. So the indices for both the contents seem very similar. Because of that, let's maybe go to one of the sections that is the same between the two. Maybe we'll do memory, which is 243 in this book. 243. I just want to get a feel for the difference. Okay. So pros, we got allocators, slab allocator, caches, kernel, libc allocator, or my own allocator. Okay. Kernel log, kernel statistics about memory usage, VM stat, hardware statistics and sampling, BPF tools. So a little bit of umkill, memleak, mmap snoop, burk stack, shared memory snoop, faults, VM scan, DR Snoop, Dr. Snoop, Dr. Snoop, Snoop Dogg. Oh, and then some exercise at the end. Okay. It's a good feeling for what is available in this book. Now I go over to his other book. This is now Memory 303. There we go. See, it starts off with more concepts This is memory fundamentals, virtual memory, paging, demand paging, overcommit, process swapping, allocators. There's more dedicated towards concepts, it seems. There is similar diagrams. Yeah, this diagram is identical. Okay. Okay. So it seems a little bit more is applied to concepts, but there's a lot shared between the two, in diagrams and content, it seems. I guess publication date. So it's the second edition. If we look here, I think this has a later publication date because it's a second edition. It says copyright 2021, but I think it's because it's a second edition. Then this one is copyright 2020. So this book originally, the original first edition was, I think, 2016 maybe. Whereas it has a 2021 second edition. This is 2020. Let's maybe go to his website and see if he can give us some more information about the two books. So BPF Performance Tools and Systems Performance Enterprise in the Cloud. Pull these out from one another. This guy and this guy. So much light. Okay. Brendan Gregg's blog, Systems Performance Enterprise in the Cloud, second edition. 8 years ago, I wrote Systems Performance Enterprise in the Cloud, also known as SysPerf book, on the performance of computing systems. And this year, I'm excited to be releasing the second edition. The first edition was successful, selling over 10,000 copies and becoming required or recommended reading at many companies and even mentioned in job descriptions. Thanks. Which job description? I'd like to know what companies. The Muse, Affirm. Thanks everyone for the support. I've received feedback that is useful not just for learning performance, but also for showing how computers work internally, essential knowledge for all engineers. The second edition adds content on BPF, BCC, BPF trace, perf, and ftrace. Mostly removes Solaris, makes numerous updates to Linux and cloud computing, and includes general improvements and additions. It is written by a more experienced version of myself than I was for the first edition, including my 6 years of experience as senior performance engineer at Netflix. This edition has also been improved by a new technical review team of over 30 engineers. How much has changed since the first edition? It's hard to say, but easy to visualize. As an example, the following shows chapter 6, CPUs, where black text is from the first edition and color text are the updates. This is a color scheme I used to show reviewers when text was changed. from oldest changes to newest: yellow, green, aqua, blue, purple, red. Of course, he has like a visualization of it. That's his like game, is visualizing using colors and shapes and stuff. Yeah, quite a bit has been updated for sure. Here is the entire book as a 31 megabyte JPEG. That's awesome. Note that the visualizations are not final, as I'm still making updates, and this doesn't highlight, figure, and copy edit changes. The book will be released in November 2020 by Addison Wesley and will be around 800 pages. It's already listed on Amazon.com. A year ago, I announced BPF Performance Tools, which is this guy here. Is that the same link or a different announcement? I guess it's a different announcement here. We'll put that in the reading list here. In a way, Systems Performance is Volume 1 and BPF Performance Tools is Volume 2. SysPerf provides balanced coverage. I wouldn't really say that they're Volume 1 or Volume 2 from reviewing them myself, just looking at the chapter on memory. A lot is shared between the two books. So it's odd that he says that, because the content is very similar from what I just, the cursor, the shallow overview that I did of the content, it seems very similar with similar diagrams and similar structure. But let's continue reading here. SysPerf provides balanced coverage of models, theory, architecture, observability tools. Models, theory, architecture, observability tools, traditional and tracing, experimental tools, and tuning. The BPF tool book focuses on BPF tracing tools only, with brief summaries of architecture and traditional tools. Which book should you buy? Both, of course. Since they are both performance books, there is a little overlap between them, but not much. I think Systems Performance has a wider audience. It is a handbook for anyone to learn performance in computer internals. The BPF Tools book will satisfy those wishing to jump ahead and run advanced tools for some quick wins. That's the vibe I got, yeah. For more information, including links showing where to buy the book, please see its website, Systems Performance Enterprise and Cloud. Okay, that's the website that's analogous to this one. So this is his other blog announcement. BPF Performance Tools Linux System and Application Observability Book. BPF eBPF Tracing is a superpower that can analyze everything. And I'll show you how in my upcoming book, BPF Performance Tools Linux System and Application Observability. Coming soon from Addison Wesley. The book includes over 150 BPF observability tools that you can run to find performance wins and troubleshoot software, and also shows you how to write your own. Over 100 of these BPF tools are newly developed from this book. You can see many of them in this diagram. That's his favorite diagram. I've been following it for a while. Hey, what's up? I am reading the book summaries and announcements for these two books, Systems Performance and BPF Performance Tools. They both have a lot of overlap, or I wouldn't say a lot, but they have a good amount of overlap. The BPF Performance Tools is like more faster time to dopamine if you want to just get stuff up and running, whereas Systems Performance is more about theory of like the performance stuff. All right, so I found this diagram to be a useful reminder and checklist when debugging production issues at Netflix, and I have printed it on a wall so I can glance at it. You may find it helps you too, which is why it is on the cover. Is it? Oh yeah, of course. Since BPF does so many things, it is becoming a technology name and no longer an acronym. It originated as Berkeley Packet Filter, an in-kernel execution engine that processes a virtual instruction set, and has been extended, also known as eBPF, for providing a safe way to extend kernel functionality. BPF is in the Linux kernel. Wire Yearbook. BPF is a new in-demand technology, and I expect that over time a dozen or more books about it may be published. It happens for for other hot new technologies. Guess how many books there are about Docker? I lost count at 30. Some other future BPF books may be good, and I'll recommend them as appropriate. To answer the question why you should buy my book, it is about using BPF for performance analysis, and is written from a veteran performance engineer and technical writer, myself. At over 700 pages, it covers CPU, memory disks, file systems, networking, multiple languages, applications, containers, hypervisors, security analysis, and the Linux kernel. It contains over 150 tools, often with source code, including over 100 brand new tools, mostly developed by myself, so that you can get started right away finding performance wins in any of these areas. It also covers over 30 traditional tools, IOStat, perf, etc., so you can use the right tool for the job, even when that tool is not BPF. It goes far beyond what you can find online, which I previously summarized. Learn EPF tracing. Is this like a little summary page? Yeah. It focuses on the recommended BPF tracing front ends, BCC and BPF trace. I don't remember I have saw this section, Wire book and other books. Yeah, I'm doing a little bit of research before I dive into the book because, well, first I want to make a choice between which book I want to read. They're both by the same author. They're both very similar in what the materials they cover. This is his blog post that announced it, and then he also has these pages dedicated to the book itself. So I figured I'd just do this reading up front to get a good idea for like what I'm getting into before I make a decision, because they're both about 800 pages. I said, yeah. So this one's about 800 pages, and the other one is about 750. So it is a bit of a commitment taking on one of these. And so I want to make sure I'm making the right decision up front. So it's good that he wrote this blog post. Give you a little bit more information. The other book that we were reading before, the Linux programming interface, he has like a similar section on his website. I don't think he has a Y, but he did have like a similar content on his website, which is nice. Let's see here. It shows production screenshots and uses cases from a major site, Netflix, including gotchas we've hit in production, such as fixing stacks and symbols and managing overhead. It was developed with the help of many members and leaders of the BPF community. I've been helping lead BPF observability since 2014, and I'm a major contributor and maintainer for the front ends. Among other things, I created the tutorials and reference guides. This is also my fourth book to cover tracing. Oh yeah, he did write books before these two. I forgot about those. They're more specific to Solaris, if I remember correctly. I was previously a professional technical trainer for Sun Educational Services, where my classes included dtrace, another tracing tool similar to BPF tracing. Tracing is adding instrumentation points to programs that are running to collect information about them. That's the way I would describe it. For example, when a function that you have in your program, when it gets invoked, that entry, like that's a place where you can instrument before the function is ran, but when it starts running, but before it has completed running. So entry and exit of your functions are places that you can instrument for tracing. And then what would you collect if you could collect information from those invocations? Arguments, stack traces, latencies, like the timing between start and end, like that delta is like timing information. So you can use tracing to figure out what's going wrong with your computer, basically. Let's see if I did a good job explaining that. We'll ask ChatGPT here. What is tracing in the context of BPF and Linux? Yeah, it's basically what I said, like adding instrumentation to a program to observe what it's doing. So you can add your own instrumentation to your programs by adding to the source code, but tracing is more about once the program's already running, how do you attach to it and observe its behavior? So what type of syscalls it's making, what type of function calls it's making, that sort of thing. Is it running? Like, is it on CPU? Is it blocked on I/O? Like that sort of thing. What type of files it has open? It's basically like he describes this BPF as what does he call it? Power, superpower. Yeah, BPF tracing is a superpower that can analyze everything. That's one way to explain it. Yeah, so it lets you answer questions like what syscalls are being called, why is this function slow, what's allocating memory, why is network latency spiking, which process triggered in a kernel path, and what, let's see, I forgot the function you told me, something like btrace, which we used to check what was happening behind the curtain. Yeah, exactly. I used, basically the main tool in this space is something called BPF trace. And it's part of the IO Visor set of tools. But I guess they have like a website, bpftrace.org. I think the B is now like the eBPF branding now. Let's see what this thing does. So the thing with BPF trace, it's heavily inspired by dtrace, which is a program for Unix outside of Linux. It doesn't run on Linux. What's the same for Windows might be? I don't know. That's a good question. What is the equivalent tool similar to BPF trace, but for Windows? I mean, I should know that. ETW, xperf, logman, custom tools built on trace event. Event tracing for Windows, ETW. I mean, I'm not a Windows person, so this is something you might want to look into more, but it looks like it's called event tracing, and this is the portal. Consuming events. Let's see, conceptual mapping. Does it allow you to run code inside the kernel in a sandbox? No. So while this might be a equivalent on Windows, one of the big advantages, let me bust out a Excalibur here. So one of the big advantages, so I'm just gonna draw a little diagram here. Can I? Yeah, okay, so this is gonna be kernel. mode, or some people call it kernel space. Let's jack this text up. How do we get that higher? This guy? Yeah. Extra large kernel space. Cool. And then over here you have things like libc, and you'll have things running on top of this. Wow, this is getting out of control. Maybe I can make this a little bit smaller. We'll do it like this. You got libc running here. And then you'll have other programs that don't rely on libc, like Go applications. So these things are applications that just talk directly to the kernel. They don't rely on libc. But a lot of software relies on libc. So we'll just say application here. I say Go because most Go applications, or a lot of them, disable libc and compile complete static binary. So this is all code that runs in user space. So I guess I should copy this, make a little diagram here, call this bad boy user space. There we go. Boom. User space. And this boundary between these two things, this is the syscall boundary. Syscall boundary. And so all operating system kernels pretty much have this broad architecture. So Windows is the same. It has a kernel. It has DLLs. So I guess in Windows you would call these, like, in Linux they're called .sos. In Windows they're .dll. Applications, these would be things like in Linux they don't have an exception, but .exe. On Windows, on Linux just plus X, chmod plus X. And then, yeah, same thing over here. I'll do a little hard break here. There we go. So yeah, this is the whole kind of like broad architecture of an operating system and programs running on an operating system. What eBPF allows you to do is run your own code inside the kernel. And that might seem scary, but it's in a sandbox. So this is sandbox. eBPF is not just like raw machine instructions. It is like a specific instruction set architecture for, I guess you'd call it a bytecode instruction set, that then gets compiled once you insert it into the kernel into native instructions. And it goes through this thing. It's like a validator that's in the kernel that validates your programs. So you'll make syscalls. There's actually a syscall. I'll actually bring it up here. man2 bpf. So this is the actual syscall that allows you to like send stuff to the kernel. If I do man syscalls here and search for bpf, you can see it's right here. So there's a dedicated syscall for it. It basically allows you to run code inside the kernel. And why would you want to do that? Well, crossing the syscall boundary is really expensive. It incurs like something called a context switch. Oh yeah, cool, no problem. Recently, I was trying to get deep into how antiviruses are working on Windows. I started with Malwarebytes, but there wasn't much on internet, so I moved to Windows Defender. All right. Well, that's story time. So BPF trace was inspired by awk, and well, I guess dtrace, and dtrace was inspired by awk. So it looks very much like awk. So you say, hey, at the beginning, just do like this code called print hello world, and it does that. But then you can also like attach to trace points. So syscall, sysenter open. So when open is called, we just log out the PID, the file name, and now every time a file is opened on the computer, it gets logged there. Cool. All right, let's continue reading about this. Bum, 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 bum. It was developed with the help of many members and leaders of the BPF community. I've been helping lead BPF observability since 2014. I'm a major contributor and maintainer of both front ends, blah, blah, blah. I was previously, we already read this. I learned firsthand how to bring beginners from different backgrounds up to speed. Early courses covered only the dtrace language and expected students to figure out what to do with it. I found it was more effective to teach by example, explain the goals and targets for performance analysis, and then share real tools to meet those goals and how to develop new ones. I found this proven approach in my book. I've taken a break from training, but I have an opportunity to start again at Netflix. I'll be using this book as materials for internal BPF course. This course will be internal only. You'll need to join Netflix to attend my class, although I'll submit a short version for Usenix's Lisa SRECon. Cool. All right, BPF trace for the win. We, the BPF community, began planning this book in 2017 and posted an announcement about it so that anyone looking could find it. At the time, BCC was great for complex tools, but it was still in development and changing. Also, no higher level front end had been completed, but we knew we needed one beyond BCC. Since then, BCC has largely stabilized, and BPF trace has become a mature, high level front end, one that is built from the ground up for BPF. BPF trace is already in use for production analysis at companies including Netflix, Facebook, and Shopify. It allows tool source to be so short and concise. It can be included in the book in its entirety. It's like including pseudocode that you can run. The last 9 months have been hectic as I and others have added features to BPF trace, fixed bugs, and stabilized the API. Hey, I'm back. So they're storing, let me highlight there. So they're storing all the rules in a MDB extension file where there are all the rules regarding scans. I don't know about that extension yet. Apple iTunes use that for backups and data storage. Yeah, so like with BPF trace, I was just showing off a program while you're away that was in their demo, and it kind of demonstrates what it's capable of. So you can like add a trace point for the syscall, for the open syscall, and now this literally traces every process, anything calling the open syscall on the entire computer. You're now capturing the PID of that process and the path that it's opening. So there's programs that he has written, like if I go up to here, if you look at file system here, or maybe VFS, there's like these snoop programs. I like the snoop programs because they allow you to snoop on stuff. So open snoop is one that allows you to like monitor opens. So you can see here, the red box up here is all the user space, and then all these boxes down here are the kernel space, and then this is a syscall interface. So open snoop is just a program that allows you to like monitor all the open system calls. Just one of the many tools that he has written here. Yeah, you can analyze a single process. You can analyze all the processes on the entire computer if you wanted to. And what's really nice about BPF is because it runs in the kernel. Let me pull up that diagram again. Because it's in this kernel, the cost of instrumentation is very low. So a lot of times monitoring events on a system with something like ptrace, you're limited to a single process, and the cost of instrumentation is very high. So you don't really want to do it in a production system unless it's absolutely necessary. But with BPF and BPF trace, you can create these tracing programs, hand them off to the kernel, allow the kernel to execute them, and then it just gives you the results. So it's really powerful. Powerful stuff. Yeah, so these are all the tools. Let's continue on here. The analysis of so many things unearthed many bugs and missing parts. Fixing these was good not only for the book, but also for BPF Trace. A special thanks to Mary, William, Alistair, Dale, Dan, so-and-so, and others for all your work in these months. I'm so grateful for my fiance. Could find the time outside her AWS job to do technical copy editing. Thanks also to Alistair for creating BPF Trace, Alexi, Daniel, so-and-so for creating BPF, and over 40 other people involved in reviewing and contributing to this book. A new era for Linux observability. As you'll see, this book is the start of a new era for Linux observability, the power to easily see anything and everything in production. A time where you can pose arbitrary questions of the system and it can answer them. A time where you're free to think about performance in new ways and you can fetch hard data to support or disprove your ideas. So another thing is, like, when I first started messing with BPF back in like 2018, it was still the case that not all production kernels that you encounter had the capability. Like, this is like new capability in the kernel. And since I've taken a bit of a break from BPF over the past 6 years, those kernels have all been deployed out into the wild. So now I know whatever company I join next, I'm going to be working at a company with a Linux kernel that has BPF capabilities. So it's kind of a no-brainer at this point. Amazing. So they end up creating the tool which can help them analyze and play the system behaviors to get to know them more about it. Exactly. This whole technology stack was engineered so that you can efficiently observe a running production system and understand what it's doing. Originally, the reason why it's called BPF is originally was Berkeley packet filter. And you might think, like, well, why are they using a packet filtering technology for observability and all these other applications? Well, the original use case for this technology was packet filtering, because if you do packet filtering in the user space, to go back to our diagram here, if your code for packet filtering is running in user space, it's going to be very costly, because the kernel has access to the devices and is copying bytes into its own address space. And then it has to hand the buffers off to the user space to then make a decision whether to process them or not, and then hand it back or send that decision back to the kernel. So it's a lot of copying of data between the user space and kernel. And again, this is called boundary here. This is like a brick wall. Like, you don't want to like have to go through this if you can avoid it. So BPF, Berkeley packet filter, was the first use case, and I think it was back in like the 80s or something. Let's see. When was BPF originally developed, and what were the use cases and tools using it? So I think TCP dump might be one. Yeah, TCP dump. So a good example, if you ever ran TCP dump to dump packets, libpcap, I forgot about that thing. That was on Windows. Wasn't it libpcap a Windows thing? No, I guess it was Unix. I could have sworn there was like something that a library you needed for Windows to get raw packet capture, but TCP dump, like this is an example filter. If you ever use Wireshark, have you ever used Wireshark? There's like that little text area for like adding your own filter to packets. And usually I do that after I've captured my packets. But that filter that you're adding is the same syntax as the filter that you're giving TCP dump here. And if you're connected directly to an interface, it's actually doing the filtering in the kernel itself. Yeah. So it was originally super limited because all it had to do is implement packet filtering. You take these expressions, compile them into a small packet filtering program, hand it off to the kernel. SCAPY, I'm not familiar with that. Oh, it's Python. And libpcap, which we just encountered here. Yeah. So in a production system that's doing a lot of packets, if you want to make an observation and capture a certain subset of the overall packets going through the system, you don't want to do a full packet capture. It's going to be too much data. And it's going to be really slow and slow down your production system. And so when you give that filter expression to TCP dump, you're saying just capture the packets that I'm interested in. And so that really reduces the overhead. Being able to give that to the kernel and allow the kernel to do that filtering. I'm not sure how this thing is implemented. It says that it's using libpcap. Again, I'm not really super familiar with some of the packet capture technology, but the BPF stuff, the original use case was for packet filtering. Yeah, back out of some of this stuff here. Yeah, I mean, it looks like a cool library. Let's see, scapy.net. This guy here. When they say written in Python, I'm like, what parts of it are in Python? Because sometimes, like when it's a Python package, a good chunk of it's in C. The more you push into Python into user space, though, the more slow it's going to be generally. And on Windows with npcap. That's what I was thinking of. Not libpcap, npcap. Let's ask ChatGPT. Does Scapy use BPF to filter packets at all? Perhaps via libpcap? So I think libpcap uses the BPF functionality. Oh, there's a raw sockets mode. Then the filtering happens in user space. So it probably defaults to raw sockets, yeah. So it's not going to be super performant. But there's a libpcap mode. And you can force it. If you say conf use pcap true. In this case, filter strings like TCP port 80 are compiled by libpcap. libpcap installs a BPF program into the kernel. Only matching packets are delivered to user space. Much more efficient for high traffic. Cool. All right. Let's back out of some of this stuff here. But yeah, thanks for sharing that. I wasn't aware of Scapy. It seems like an interesting project, but I wouldn't trust it by default for high performance situations because it looks like it uses raw sockets, which is like, and copies data into the user space. All right, so isn't BPF still evolving? It is, but I had a static goal for the book to get to all the included 150 tracing tools to work. After many months of development, we've reached that milestone. I've also involved the main BPF developers so I could document their planned work to make this book as future-proof as possible. BPF type format. Yeah. This is something that I wonder if this has landed yet. So BPF type format is kind of like the technology in dtrace that allows you to basically describe all the kernel data structures in a format that's attached to the kernel so that you don't have to bring all these kernel headers with you when you do BPF stuff. So BPF type format is the only large change expected for tracing in the nearest future. It will provide kernel struct information beyond the Linux headers package and is summarized in the book. A few other tools declare missing structs as a workaround, and some years from now it will be possible to remove those workarounds. What I expect to break sooner is the kprobe based source code in the book. Kprobes is considered an unstable API. It's a cool API. Uprobes and kprobes are both cool, but they have their downsides. So kprobes is considered an unstable API as it instruments kernel functions, and a kernel engineer may rename a function in a later kernel, breaking the tool. This is why the tools use the stable tracepoint interface whenever possible. But it's not always possible, and this is the nature of tracing. It is not, however, the hardest problem you'll face. The hardest problem is knowing what to do with BPF tracing, and even broken tools are a source of useful ideas. I will create a GitHub repository for the book's tools as is, plus updated versions, and allow everyone to submit updates as they are found to be needed. What about systems performance? System performance has sold very well, thanks everyone. It's recommended reading for new hires at several companies, including some teams at Facebook and SUSE. It is the encyclopedia of performance covering many topics with a balance of theory and practice. BPF performance tool focuses on one topic only, observability, and goes deeper. The BPF book is about doing analysis right now. With these tools and capabilities, now that I've finished it, I can do a second edition of Systems Performance not right away. Good luck. BPF is the hot new technology, and it is an extreme privilege to have written the book on it. I was determined to give you the best book imaginable and not waste this opportunity. I hope you enjoy it, and it helps find you valuable performance wins. Good luck. The URL for where the book updates, please visit my BPF Performance Tool book, discussion, Hacker News. Boop. Okay, so these are 2 pages now. So this is the updated second edition, and then this is the book that we just talked about. All right, well, let's go ahead and, since we already read a page on that one, let's read this page over here. This is the official site for the book Systems Performance. Yeah, I mean, this is more focused on BPF tools and getting like quick wins in like production environments, which, you know, will get your dopamine flowing more, which is actually a good thing. And then system performance here, I think it's more theory. I think he says there's a balance between theory and practice, but I would say this one, the performance book, is more focused on theory and performance in general and how computers work. And then BPF Performance Tools is specifically Linux BPF technology, how to get quick wins and get dopamine. So I'm leaning towards doing this one first, even though he said like it's a sequel basically to this one. I'm leaning towards doing the BPF Performance Tools one first. I think moving from tools and then to performance will help one to make new tools, possibly. Okay, let's read this. So this is official site for the book System Performance Enterprise in the Cloud, 2nd edition, blah, blah, blah. Blah, blah, blah. First edition was very successful, becoming recommended required reading in many companies and has sold editions. I've had many emails from people studying the book for Facebook engineering interview. I'm glad it's helpful. There's also a companion book, BPF Performance Tools, that provides advanced coverage of BPF performance analysis tools. On this page, what's news, why operating systems, audience differences, terms of blah, blah, blah. Okay, sample figures. Okay, I've already looked at some of these. What is new in 2nd edition? 2nd edition adds context on BPF, BCC, BPF trace, perf, and ftrace. Mostly removes Solaris, makes numerous updates to the Linux and cloud computing, and includes general improvements in addition. Since writing the 1st edition, I now have over 6 years of experience as a senior performance engineer at Netflix, working on new technologies with other engineer experts. This experience has helped me improve this book. My blog post about the book includes visualization of every page with text colored to show what has changed. Chapters are structured to first cover durable skills, models, architectures, and methodologies, and then implementation with tools and tuning. This will be evident to those who read the 1st edition. Most chapters begin with only light changes since the 1st edition, but the changes increase as each chapter progresses. Why system performance? System performance is an important skill for all computer users, whether you're trying to understand why your laptop is slow or optimizing the performance. This applies to your VM. Or optimizing the performance of large-scale computing environments, for example, Facebook's data center or Netflix cloud. Systems performance is the study of application, operating system kernel, and hardware performance. There are 2 general goals: improving price per performance. So you want to lower price and improve performance. So the numerator should go down and the denominator goes up. So that means that the total value of that goes down. Reducing latency outliers. Most engineers don't really look at latency outliers, to be honest. Latency outliers are someone else's problem, and they're the worst thing for user experience. But they don't show up in most averages of latencies and stuff, so they're not obsessed over as much. Other activities of systems performance include benchmarking to evaluate systems, capacity planning, bottleneck elimination, and scalability analysis, so that you'll discover scalability limiters early in time to fix them. Operating systems topics are included in an OS agnostic way, then Linux is covered as the primary example. Audience. This book is primarily for system administrators, system reliability engineers, performance engineers, support staff, and other operators in enterprise and cloud environments. It is also a useful reference for developers, database administrators, and web server administrators who would like to understand operating systems and application performance. Why this book is different. While it covers performance tools and background for understanding them, what makes this book different is the inclusion of many performance methodologies, including those covered briefly by my Usenix 2012 talk. It would be nice to watch that. I've been teaching and developing systems performance classes on and off for over 10 years and have found methodologies to be critical for giving students a starting point and then guiding them through performance activities. The USE method is a methodology I developed for this purpose. I already ran over the TOC, and the rest of this stuff is not interesting to me. So, this page has a good amount on it. Let's go ahead and read this. BPF performance tools. So I think this will be cool as one can make custom API and integrate all these tools and then digest that to monitoring tools. Yeah, so the book, this BPF performance tools, he explicitly calls out, if I look at the table of contents, wow, there's other Chinese edition. Amazing. If you go, actually I have the PDF here. Let me just open it up. That probably doesn't belong there. We can just shift delete it. Boop. But if I go to downloads, this one. So I was reading the back cover of it, and he talked about the section on, where was it? kubectl trace, PCP, and Grafana. So let's just search for Grafana. It seems to be around 709. Sure. Can I get out of that, please? And then this thing, go away. Thank you. There we go. So he shows the Netflix dashboards and stuff, but there's a Grafana thing. So Grafana is just like a really popular like dashboard observability tool. If I just go to images here, you can see what it looks like. Looks like that. Yeah. So this is using Grafana, connecting and viewing data using this thing called Grafana PCP Live. So one of the things, oh, you use it. Okay, cool. One of the things I was thinking about doing as part of reading this book is setting up a home lab of sorts, a Kubernetes cluster. I say home lab. It would just be 3 virtual machines running on my framework desktop, and just setting them as if they're like, you know, like an actual Kubernetes cluster. And just using something like Kops or whatever to spin that up, and then installing Grafana, and then capturing data and you're using BPF trace and sending it into Grafana. I think that would be a really fun exercise, and document it all and, you know, publish it online so that we can like hack on it. You know, I think that'd be a cool little project. This is the must book for me. Yeah, so there's a PDF. I mean, I purchased the book. I highly recommend you purchase it, but in absence of resources or availability, there's a PDF on GitHub. And it's color too. It's in color. It's really nice. Let's see here. Cloudflare eBPF Prometheus exporter. Yeah, I mean, there's a lot to have fun with here. This kubectl trace thing, I have a commit against this thing. I was at I think it was a Google Cloud Next conference. I gave a talk there when this was announced, and I was like working on my own Kubernetes BPF tracing tool, and they announced this. I was like, they got there first. You've yet to work on Kubernetes? Yeah. Well, I guess that'd be a fun project to hack on then, because I have a lot of Kubernetes experience, so it'd be nice to share some of that. Yeah. Earlier on in my career, I did a lot of conference talks. I've talked at KubeCon several times. Where else? GopherCon, the Go programming language conference. I used to go to every GopherCon. I went to every GopherCon until COVID happened, and then I kind of lost the desire to want to go to conferences after there's a global pandemic. So stopped going after that. Actually, I gave a workshop on some stuff at GopherCon that year during the conference. But yeah, doing like a Kubernetes cluster locally here, installing all this stuff, getting it all traced and wired together, I think that'd be a really cool project. So that's why I'm leaning towards this one, because it's more like it's a shorter path to dopamine. And I feel like the books that we've been reading while I've been learning a lot, it hasn't been a lot of like high dopamine stuff. So I think I'm going to go with this book first, and then the other systems performance book I'll just put somewhere else for now. And let's go ahead and pull up our repo here. I'm going to jump to learning log. Oops, sorry. Yeah, there we go. Vim readme. And I'm going to get the BPF performance tools, and I'm going to bring that up to the top here. So that'll be the one that we're working on next. And then while we're at it, I did pull up this conference talk. I figured it's getting a little late. This is an hour and 30. That'll take me to what, like 9-ish? So I think what I'll do is I'll watch this on 2x. And we will see if we can keep up with it. But I'd like to watch this before I log off tonight. So, oh, is this going to be a problem because
thank you. And,
the audio is not in sync?
And thanks for the introduction, Doug. That's right. I infamously have become known as Shouting Guy. I hope some of the other accomplishments of my career are more interesting than that. But
maybe we do 1, because he speaks pretty fast. Let's try 1.5x.
that's fine. It is quite an amusing video. How many people have seen that video, by the way? The shouting at. Okay, so most people.
Okay,
know
that.
So I am actually.
What might be cool is write a complete blog and the local lab all written that I can set up in any PC for readers to test themselves. Yeah, that would be cool. I was thinking about using KVM to spin everything up on Linux, but there's no reason why you couldn't do it on like a virtual machine like VirtualBox or even VMware. 7:50 a.m. there. Cool. Well, you got your whole day ahead of you. I'm starting to sunset here. What I'm going to do is I'm going to try to get both of these. So I'm going to mute it on my computer here. I got to debug the latency issue. I'm going to pull this up on my stream machine and see if I can get it going at the same time here. Lisa 12 performance analysis methodology. See if we can pull up the same video here. And then I'll set this to be 1.5.
Well, thank you. And thank you for attending my talk, and thanks to Lisa for inviting me for another talk.
Okay. Oh.
And thanks for the introduction, Doug. That's right, I infamously have become known as Shouting Guy. I hope some of the other accomplishments of my career are more interesting than that, but...
Okay. Okay, we'll go over here. I hate it when this freaking thing gets all out of sync here. Okay, there we go. All right, I'll hit play here, and then nope, I didn't hit the right button.
And thank you for attending my talk, and thanks to Lisa for inviting me for another talk. And thanks for the introduction, Doug. That's right, I infamously have become known as Shouting Guy. I hope some of the other accomplishments of my career are more interesting than that, but that's fine. It is quite an amusing video. How many people have seen that video, by the way, the shouting at... Okay, so most people in the room. So I am actually Shouting Guy. This talk, I'm going to talk about performance analysis methodology, in particular the use method. This is a new methodology that I've developed to help people find bottlenecks and errors on systems. And an article appeared in ACMQ this morning that I wrote covering the use method. So much of this presentation is based on that. I'm a lead performance engineer at Giant. I work on performance tools. I've written many in the past. Some people might know me from tools like IOSnoop, which is installed by default on Mac OS X. I wrote the dtrace toolkit. I've written a lot of different performance tools. More recently, I've done visualizations, such as heat maps for analysis, and methodologies. I was Brendan at Sun, Oracle, and now Giant. Just to mention what Giant, my company, does, we're a high-performance cloud infrastructure. We do public and private clouds. We have OS virtualization for bare metal performance, which works fantastically well. We do have KVM for Linux guests, and we're the core developers of SmartOS and Node.js. Something that I guess isn't on the slide is that we have a lot of people who come from other providers and who are running other operating systems. And since we tell people we're the high performance, it's actually the tagline at the top of the Joint website now, we're the high performance cloud infrastructure, many of our potential customers say, well, prove it. Make this operating system go faster, make my applications go faster. And I come from an enterprise world, and it's very different in the cloud world. People get to change very rapidly. And so in the enterprise world, you might have to go through a proof of concept. It can take days, it can take weeks. This can be all done in an hour in the cloud world. So the rubber meets the road very fast, and you have to prove that you can deliver performance very fast. And this is, now that I'm working on this in the cloud, I've been able to work on performance methodologies at an increased pace, much faster than I did in the enterprise world. At Lisa 10, I talked about performance visualizations. So that included latency heat maps, including crazy ones like the latency pterodactyl, which I still don't understand every single feature of, but understand most of them. And this year I'm talking about performance methodologies. I've been studying them quite a lot for an upcoming book, and this is the first time I've mentioned this publicly. Next year I have a book with Prentice Hall called Systems, Performance, Enterprise in the Cloud, and it's fantastic. I get to write a lot more about methodologies and tools and visualizations for both of those environments.
This is just background.
Funnily enough, the primary operating system for this book will be Linux, and then Solaris-based operating systems are secondary, because that's especially in the cloud world, there's a lot of people running Linux. Although the methodologies are actually common. And the methodologies I'm talking about in this presentation doesn't actually matter if you're Linux or SmartOS or FreeBSD or Mac OS X. It's going to be the same methodology. So what I'll talk about, I'll start with a performance issue example. And then I'd like to go through 10 performance methodologies and anti-methodologies. And in particular, focusing on the use method. And I put in the slide deck, the content is based on an article that just got released today. And I've also done a lot of research into methodologies for Prentice Hall. And I've also done a lot of research for methodologies. I'm teaching classes again. I used to teach classes many years ago in systems performance. I'm now doing that again. And actually teaching people, fix this problem, and here is a methodology you can follow, is when you get to find out whether it works or not. Because if the student can't fix the problem, in some ways it's not their fault, it's my fault for not giving them a good enough methodology to go to root cause quickly. And so I've been able to put a lot of these methodologies to the test by giving people simulated issues and seeing if they solve it. And being very pragmatic about it and understanding that it's my fault if they can't solve it. I need to help develop these methodologies and provide that guidance. The content in this talk does have a focus on systems performance, but it's also applicable to applications. So to start with, as a performance issue, and this was one that happened recently, and it's also happened very similarly more than once. The database response time sometimes takes multiple seconds. Is the network dropping packets? The customer tested the network using traceroute and found that, yes, indeed, the network was dropping some packets. So if you drop a packet, then you have a retransmit. If that happens during a query, that can add 1 second of latency or 3 seconds of latency. It depends on the retransmit interval. So this seems like a fair hypothesis. We have a performance support chain You have people at the first level who look at the tickets and try and resolve them. We have at second level people who have expertise. I kind of end up with all the too hard issues that no one else can fix. At the first level, they ran traceroute, but they couldn't reproduce the issue. At the second level, they looked at the network and said it looked fine. And while they were logged into the systems, they checked CPUs as well. Now, the customer description didn't mention CPUs. The notion is
So 2x my
the
mind
idea
is more
this
focused.
Is an ad hoc checklist that those support staff did because they've commonly hit issues of CPU.
Do you want to go to
especially
2x?
This is a cloud computing environment.
I can do
so
that.
While they're there, while they're looking into the systems, I'm going to check some other recent issues and see if it's any of them as well. Even though the customer didn't mention them.
Let's go to 2x. Takes me a few seconds to get this thing synchronized.
Because that proves successful. So they checked a few other things, like CPU said, that looks okay. Doesn't actually look like there's an issue. And so now it's my turn. Capture every single packet that went on the wire and then analyze that. I can analyze that using Wireshark and various other tools, Ethereal. There is performance overhead during capture. That's the CPU cost of instrumentation and the storage cost of saving it. And also moving it around. If I'm putting it on a server, I need to move it to my laptop for analysis. There's more network traffic I need to do. Also, try doing this on a very busy 10 gigabit network. You have very large files very quickly. It starts to become prohibitive. It's time consuming to analyze. It's not real time. I like doing it. I'm good at doing it. I used to do this a lot in the past. Nowadays, I do a lot of dynamic tracing of the TCP/IP stack. Here, it's efficient. I can only trace the drop and retransmit paths. I have access to the kernel context, so it's not just what's on the wire. I can look at the TCP state. I can look at various counters that the kernel has in its brain that you don't see on the wire that might explain why connections have been problematic. A lot of those counters, by the way, they're exploited via SNMP. So there's standard nibs for these counters. Plus, there's internal ones you don't normally see. It's real time. Just as an example script, this is a dtrace script, TCP listen drop, and I can see which SYN packets were dropped. And the source, I can get the destination IP address, the timestamp. SYN packets get dropped when you reach the end of your TCP backlog, which is why we tune the thing. And that will happen if you have a burst of load. So I love doing this. I love going into the TCP stack and dtrace and understanding things and solving problems. And so here's a customer who has an issue. I've got network packet drops. I have query latency. It comes.
I agree. It's a little bit too
I just do this
fast.
stuff.
I wanted to try it though because you said that you were down. All right.
Which is really fun, but instead, I began with a methodology. Instead of doing all the really fun stuff, let's do a methodology to check the system, check basic system health before I go down into the TCP/IP stack, because that's worthwhile. I used the use method, which I'll be covering in this talk, and in 5 minutes I found that the CPUs were okay, just like support had already found. The network was okay, just like we suspected, but memory was exhausted, and the system was paging. In Linux, you call this swapping. And the disks had periodic bursts of 100% utilization. These are serious issues. If the system's paging, and I could see that it was paging the application, that's likely to be your performance issue. They had been overlooked because the customer had talked about networking, and people had a target fixation on the networking issue. The customer was surprised by my analysis. Are you sure that I had these drop packets? And I was able to then prove it using a different methodology, using a latency analysis. And so for latency analysis, on this particular system, I had microstate accounting and dynamic tracing available. So microstate accounting, I can look at the time the application was blocked doing anonymous page-ins, because there's good page-ins and there's bad page-ins. Anonymous page-ins are the bad ones. This means you've been paged out because you've exhausted memory. And so I can look at the time that the thread was blocked on this. This is not just some counter, this happened. Yes, you were actually blocked for 100 milliseconds on the anonymous page-in. This only happens because you've run out of memory. And so this is a very good way to confirm that that has hurt the application. And also for disk, I looked at the synchronous latency of the application to the file system interface, and there was 1,000 millisecond fsync calls, which were happening in application context. That's slower. So digging this stuff out took me about an hour, only because these are actually very common. Running out of CPU and needing to, running out of memory and needing to look at anonymous page-ins, having disk issues and needing to quantify that. It's something I do very often, so I can get that done in about an hour. Otherwise, it'd take half a day. But it's different to the previous methodology. The use method, I can go through that in 5 minutes and just give you that first pass of system issues, and then I can use a deeper methodology like latency analysis to confirm it and to quantify it. So methodologies can help identify and root cause issues. Different methodologies can be used as needed. In this case, I use those two. It's a faster resolution of issues. It frees time for multiple teams. We often find that once you find the location of an issue, that means the other teams involved can go home. Normally, you have this performance crisis where you have the database team online, the sysadmin team online, the application developers online, the OS engineers online, it's usually myself. And once you find the location of it, the other teams can go home. And so having a faster resolution of issues, it's not just fixing the issue. It's about freeing up time for all the staff involved. And that's why quantifying is important, because you cut through this sort of political blame game. Once you quantify it, then you know for certain, and you can then go and it gives management the power to invest in fixing that solution, gives them the numbers they need. So performance methodologies, I normally give tool talks. I normally talk about performance analysis. I love it. I love using dynamic tracing. The existing tool set is why I co-authored SLAS Performance and Tools. But methodologies, it's not a tool. It's not a product. It's a procedure. It is a documentation. And it's a procedure that I can include in the slide deck. I put in the ACM article this morning. You can build tools to help. So I could build a tool to facilitate the use method and a tool to facilitate latency analysis. It could also be products. So if I'm purchasing monitoring solutions, that could be part of the product. It could give me a use method wizard. The audience for methodologies, for beginners, it provides a starting point. One of the hardest things with performance analysis is where do I start? I have this issue. I know my environment is hugely complicated. I have databases and the application tier, and then the caching, and load balancers, and the storage arrays. There's a lot of components. I don't know where to start. I don't know what tool to begin running. So methodologies give you a starting point. For experts, it's useful as a reminder. I like the methodologies because I forget things, and I can use them to refresh my brain and to remind myself, yeah, I should stop this methodology. It's not working. I should try drill down analysis instead. I should try workload characterization instead. So for me, it's a reminder.
I have test performance of
Casual
apps,
users,
but never
there
on
are a lot of
system
people in
level.
between. There are a lot of people who are...
Sometimes the
developing.
system is the problem.
Performance is not my day job, but I need to know enough. I'm doing sysadmin. Performance is not my day job, but I need to know enough. And so methodologies provide you a checklist. So something you can step through, and let's just check that I've gone through the basics and found the egregious issues. Operating system performance circa 90s was metric orientated, where the vendor created metrics and performance tools, and the user developed methods to interpret the metrics. I did a lot of performance analysis in that culture. And the previous common methodologies focused on ad hoc checklists of common tuning tips, tool-based checklists, which seem to make more sense in some cases, where for every tool, you then say these are the useful metrics, and this is how to interpret each metric, and these are the actionable items based on the interpretation. And there was another methodology, which was the study kernel internals and then develop your own. And it gives you a great understanding of the system you're trying to analyze, or study application internals, for that matter. But that takes a lot of time. There is a common problem to all of this, and that was vendors didn't always provide you the best metrics. And the metrics they provided were often incomplete. And it's very difficult as a consumer to have this epiphany that the operating system vendor or the application vendor who wrote this software, who knows it inside out, who has a bug database of all sorts of weird issues that I would barely understand a tenth of them. It's hard to imagine that they haven't given me the best metrics, that there's areas that are missing that they haven't included as part of the product. But this happens a lot.
I turned the
Operating
volume
systems
up a
now provide
little
dynamic
bit.
tracing. So you get to see anything, not just what the vendor gave you. I get to do that using dtrace a lot. Of course, dtrace is on Solaris-based operating systems, including SmartOS that we use. Oracle has been porting it to Linux, and they had an announcement a couple of days ago. They've pushed another release of their dtrace for Linux port. And it's not the only Linux port of dtrace, if you're interested in that side of things. But there's also other ways to get dynamic tracing as well. The hardest part about using dynamic tracing, whichever tool you use and whichever operating system you're on, the hardest part is knowing what questions to ask. With dynamic tracing, I can instrument every function in my application and every function in the kernel, which is probably 100,000 different things. What do I do with it? What script do I write? Methodologies pose the questions, and so the methodology will help you see, this is the question, this is the small question I need to answer. Now I can go and use dynamic tracing to answer that question, because that's part of my drill down analysis or latency analysis. I'm studying methodologies a lot more because of dynamic tracing. Previously, without it, it would have been much more of an academic exercise. It would have been a lot of effort that I could come up with these great latency analysis techniques and procedures, but no one could benefit from them because you didn't have any tools to do it. With dynamic tracing, you have that catch-all. If the existing toolset doesn't do it, you have some means to go and answer those questions. So the rise of methodologies, at least the rise of my analysis and study of methodologies, is very much related to dynamic tracing because it means it's a practical exercise. I'm able to do this much more in production on real systems and deliver results. So, going through 10 methodologies, starting with some anti-methodologies for comparison. The first one I've got is the blame someone else anti-method. And it works like this. So for each of these methodologies, I've enumerated them, which is great if you're a beginner. It gives you a series of steps to follow. Find a system or environment component you are not responsible for. Hypothesize that the issue is with that component. Redirect the issue to the responsible team. And when you're proven wrong, go back to step 1. Anyone know any group or staff or support team that does this? This kind of sounds familiar. I have a few hands going up. This is why I called it an anti-method. This is an anti-methodology. This is not scientific. Maybe it's the network. Can you check with the network team if they've had dropped packets or something? This is a very familiar thing. I know if you're a network administrator, you must get tired of hearing this. You must get tired of being blamed without any sort of evidence. Maybe it is the network, but please have evidence. A colleague asked if I could make that methodology into a flowchart. Flowchart. Please don't learn this methodology. This is not the point of the talk.
Yeah, exactly.
Recognize and compare.
With anything that goes
Wasteful of
wrong.
other teams' resources. It's identifiable by a lack of data analysis, and in some cases, any data at all. In order to deal with it, ask for screenshots. If you're getting blamed for something, ask, show me the data that makes you think that there's a problem with the network. And you can take those screenshots to someone else for a second opinion. Say, would you conclude that there's a problem with the network based on this? Streetlight anti-method. For the streetlight anti-method, you pick observability tools that are familiar, found on the internet, or found at random.
Very familiar with that.
Run them, and you look for obvious issues. It seems to be what a lot of people don't do. In LAC, this is the absence of a methodology. Just trying to Google some things, look at Stack Overflow, let's try this, let's try that. I called it the streetlight anti-method after an observational bias called the streetlight effect. And that follows a parable. A policeman sees a drunk looking under a streetlight and asks what he's looking for. The drunk says he's lost his keys. The policeman can't find them either and asks if he lost them under the streetlight. The drunk replies, no, but this is where the light is best. Again, might sound familiar. Some of the common cases where it comes up, when someone has a performance issue where they've just run ping. Why are you running ping? The performance issue you're describing is about the storage array. Why are you testing the network? Is ping familiar? Another one where it comes up is where the customer has been running top for a very long time. They've been running top for days and they haven't progressed past top. Now, I use top, top's great, and solves a class of issues, but I use it for a very short amount of time, and then I'm using various other tools to drill down further. So why are you still running top? The streetlight anti-method is a tools-based approach. It is inefficient. It can take time before the right tool is found. It can be wasteful when investigating false positives. And sometimes, especially with, I guess, the network administration teams are now getting very, very good at this, the ones I've worked with, when they get blamed for things, because people run ping, because that's familiar. And so they can not waste their time so much by coming back and saying, no, it's not the network. We have monitoring in place. We can confirm that quickly. The streetlight anti-method, probably the biggest problem is that it is incomplete. You're missing out on various issues that the tools aren't easily identifying, especially if the tools are difficult to find or learn. And of course, tools are incomplete or missing. This goes back to, don't assume that the vendor is giving you every single metric, because often the vendor has not. Now, I've been that vendor and I've worked in the performance groups, and there's always more that we can do. And there's always like vast areas that are just missing. We know we need to add counters to this area, and we just haven't done it yet. It's a ticket in the system. So incomplete, you might be missing out on things. The ad hoc checklist method. Now this isn't quite an anti-method, because this can be useful. You have a series of steps, 1 to n. Run A, if B, do C. Each item can include which tool to run, how to interpret the output, and suggested actions. And you can cover common and recent issues. As a key example of this, Adrian Cockcroft's book, Sun Performance and Tuning, was influential. And on page 1, he had quick reference for common tuning tips, which had an ad hoc checklist, which went through 11 items. And it's interesting because he put this on page 1. You open the book and it's like, let's go. It's time to look at disk bottlenecks and run ISTAT with 30-second intervals and look for more than 30% busy disks. And went through NFS response times and memory checks and other things. These ad hoc checklists are easy to follow. They can be fast. They give you a consistent check of all items. So if I am creating an ad hoc checklist, it's great because I get to put those nasty issues in there that I know people are struggling to find. And I get to make sure the list is complete. And it can be prescriptive. It can say, do this. If you see this, do that. Which for beginners is it's taking you all the way from not knowing where to start to actually fixing the problem in the shortest amount of time possible. Which is why this can be pragmatic. This can be a process that an entire team of staff can follow to check a minimum set of issues and deliver a practical result. And I've seen this used successfully where you have a large organization says, I have this support team, they need to deal with some performance issues. They're not the performance experts, and they're not trying to be. Their expertise is with products and with other areas. But as part of their day job, they sometimes need to go through and do a quick pass of performance issue checks. And so they'll use these ad hoc checklists. The cons are probably pretty obvious. It's limited to the items on the list. It's point-in-time recommendations. It needs regular updates. And people follow these lists without really having an understanding of what they're doing. And that can be problematic as well. So the ad hoc checklist method, it has uses, it has pros. And I've included that as it is a very commonly used methodology. Problem statement method is the next one. This is used by support teams. It's when you first contact a vendor and you say, I've got an issue. Often the support team will go through a series of questions. I've seen some companies will actually send you a form. You have to fill out the answers to these questions, and that gets put into the ticketing system. For example, for performance issues, the questions might be, question 1, what makes you think there is a performance problem? Question 2, has the system ever performed well? Ever. Question 3, what changed recently? And so on. This doesn't require running any tools. This is just asking the customer questions about the issue to see if we can solve it straight away before we engage the back-end engineering team. And often this is very effective. I've got some example answers here. What makes you think there is a performance problem? I saw 1,000 disk IOPS. I've had this a lot. Great, 1,000 disk IOPS. So what? Is that a problem? Did you have 10,000 before or 100 before? Disk IOPS, of course, these days in modern systems are frequently asynchronous to what the application is doing because of features like prefetch and write buffering. And you don't have a direct path between disk latency and the application latency on purpose because we put a whole bunch of engineering into the stack to separate the two because disks are slow. So starting with disks as your problem statement is a bit questionable. And IOPS themselves, on previous rotational media, it could be sequential IOPS, it could be random IOPS. Fortunately, we're on flash media now, which don't have the sequential random issue, except for a tiny bit because of what the firmware does, and the way it does address mapping. On flash memory, instead of random versus sequential, it's more, are you doing reads versus writes, and what's the size of them? Because if you actually do 10 megabyte I/O versus 1 kilobyte I/O, or 4 kilobyte I/O, there is a millisecond difference there. So 1,000 disk IOPS, it's just not enough information. Question 2 was, has the system ever performed well? I've had this sometimes where the customer says, here's a performance issue, go solve it. And so I've rolled my sleeves up and I've dived in, I'm running all sorts of tools. And it's like, wow, this system is just terrible. There's performance issues everywhere. I can't imagine how this ever worked. And I'm trying to hypothesize, how did it break? How did it go from a working system to this complete mess that they've given me? Like, there's issues galore. And so I spend like a day or 2 days, and I go back to the customer, and I'm like, I just can't figure it out. I don't know how you got here. I don't know how you got into this mess. And they say, oh, it never worked. We just built it. It's never ever worked. We just filed that ticket. We thought you'd figured it out. It's like, thanks. It would be great to know that from the start. So yeah, has the system ever performed well? Good question to start with. What changed recently? That can be, we're on Slashdot, we're on Hacker News, we're on Reddit right now. And I've had many cases like this where, again, you're looking for like, how did the system break? And it's meta. The system didn't break. They're on Slashdot right now. And that's why there's so much load, and that's why you've got network drops, et cetera, et cetera. Important question to ask early on. And sometimes it's funny where the customer will argue and say, no, it's a problem with the operating system, or it's a problem with the applications. Like, please check if you've had a spike of load. Like, what has happened? Because that's what it looks like. Can the performance degradation be expressed in terms of latency? That's a great one because you get to quantify it. So is query time 10% slower or 10 times slower? If you put that into the ticket, that might help you say it's a P1 ticket or a P5 ticket or whatever the scale system is. Does the problem affect other people or applications? Great question to ask. So yeah, my networking for this server is a bit odd. Like, it's offline at the moment. So you spend a while, it's like, I can't connect to the server. Let's try some other, can't connect to anything. Oh yeah, the whole network's down. So important question to ask. And also, what is the environment? So whatever your environment is, it's a worthwhile exercise to go to the bug databases for all your components and search for the keyword performance. Just so you know, everything breaks. Everything has performance issues. From CPUs to firmware to databases, the operating system, the kernel, everything has performance issues. And if you are running a much older version of disk firmware or storage HBA firmware or the operating system kernel or the applications, there may be a large subset of performance fixes you don't have. That's why we asked this early on. What's the environment? Often people are following the mantra, if it's not broken, don't fix it. It makes a lot of sense in some ways. Until it is broken. It's broken because the performance is now bad. And so let's look up the bug database. Yes, that's a known issue. Let's now do the fix. Let's now upgrade it. So the problem statement method, it's often used by support staff for collecting information and entering into a ticketing system. It can be used first before other methodologies. It's fast. It resolves a class of issues without further investigation. It has limited scope. We're not running tools and diving into the system or applications yet. That's obvious. But it's a great first methodology to use. Scientific method. Some people, hands up if this is dead familiar. You taught this at school. Just curious. Wow, lots of people. So you may already do this in your sleep. Basically, the whole room put their hands up. You may already do this in your sleep, so this might be nothing new. With a scientific method, question, hypothesis, prediction, test, and analysis. The way I was taught it, we spent a lot of time enumerating our assumptions and then going through them as well, which is also useful. For performance analysis, the test stage, in order to verify the hypothesis, you can have observation tests where you run a tool and read a metric, and you can have experimental tests where you change a tunable parameter, increase or decrease load. One thing that some of the best people in the industry I know at performance are good at is having a good balance between observational and experimental. So for me, it feels like these are my two hands when I'm operating on an issue. I get to observe things, and I get to change things, and then look at the effect of those changes. Some people get really, really good at one of these, but not the other one. And if you feel like you're fantastic at experimental, I can benchmark this and deduce all these wonderful things, like perform all these tests, then try looking at the observational toolset and learning them, and vice versa. Because they're both equally very, very useful. I've got some examples so you can see how this goes together, but this might be pretty obvious. So example A, observational. Question, what is causing slow database queries? Hypothesis, noisy neighbors, because we're on the cloud. They're performing disk I/O, and it's contending with my database disk I/O. My database is using the disks via the file system. So actually, it's my file system latency that's slow. It's slow because of noisy neighbors. Prediction, okay. This is going to be observational. If file system I/O latency is measured during a query, it will show that it's responsible for the slow queries. Like this is how we can measure it and actually put it to the test. If what you're saying is true, it's noisy neighbors and they're rattling the disks and they're slowing you down, that's going to manifest it up at the file system interface, and we can measure that and prove it. I do this a lot actually because it's a commonly blamed thing. Dynamic tracing of database file system latency as a ratio of query latency. For this example, it showed that it was less than 5% of time was in the file system. So for our analysis, we can say, well, it's not the file system or disks. We need to look at what the 95% of time was and analyze that. These days, we actually have, this is such a common issue, we put ZFS I/O throttling into SmartOS so that tenants, there's actually a way to throttle I/O between them. Example B, observational. Why is an app slower after moving it to a multiprocessor system? Hypothesis, it's numerous effects. Remote memory I/O, CPU interconnect contention, less cache warmth, cross calls. All sorts of bad things happen when you start adding extra processors.
So once we host MongoDB, and after millions of requests on 64 gigabyte RAM, the CPU disk operation hits peak.
So we're going to blame numerous effects for the app being slower. For the observational prediction, there should be an increase in memory stall cycles and an increase in cycles per instruction and remote memory access. I can observe these indicators from the CPU performance counters.
I ran Mongo in production for
the test.
The last company I worked at, but we paid for Mongo to run it for us.
Read the performance counters and figure it out. For that observational test, analysis consistent with predictions. And I do see this.
I'm not a big fan of Mongo myself.
This is a thing that does happen.
Kind of fails a lot.
Sometimes experimental can shed light on that much more quickly than reading those processor manuals. Same problem, but now I've got a different prediction. How about I disable the extra processors and see what happens? So my prediction is, because it's numerous effects, if I disable the extra processors and just take it to a single socket system, then performance will be better. As a test, we disabled CPUs on extra processors, and perf improves by 50%. So experimental test, quicker than the observational test. It's not definite, but it's another clue, it's more information for you to continue your analysis. I actually do this a lot. And it comes from the scientific method. It's one of those things where I am performing a deliberate test in order to check a hypothesis. Just turning off CPUs. Of course, actually offlining them from the operating system is okay, but they're still powered on to some extent, and you're still using the memory bus, so it's not the same as ripping the socket actually out, but it will give you a clue. Example D, this is another example to go through these quickly. Degraded file system performance as the file system cache grows. Well, why would file system performance get worse as the cache grows?
It costs a lot to pay them to run it.
File system metadata overheads relative to the record size.
What's it called? Atlas?
So the cache
MongoDB Atlas?
Data in units of
super
records.
expensive.
Might be 8 kilobytes or 128 kilobytes.
This is another good talk.
So the more records you have, the more contention on various metadata to look after this cached information, such as hash tables.
Save that for later.
So my prediction is, if I make the record size, this is a real world one that I had in enterprise, where we're already using the max record size. And so we kind of assumed that this was the problem, but in order to test it, we couldn't improve performance. So we said, let's actually hurt performance as a means of proving it, because we'd already gone to the max record size. So let's progressively reduce the record size and make it worse and worse. Let's go to half it, quarter, 8, 16th, and so on, and then plot that on a graph and just visually see how much that relates to our hypothesis. And that actually results in consistent.
Yeah, it's a lot of theory, methods.
And this is back to scientific.
That's why I wanted to do this book instead, because it's more tools and technology and less methodology.
And the last one, experimental. Why did write throughput drop by 20%? Hypothesis, disk vibration caused by a data center alarm. Prediction, any loud noise will reduce throughput. How would you test that?
He yelled at the JBud.
So let's just shout at the disks, and then measuring latency as a heat map, and it coincided. So maybe it doesn't look scientific, but in some ways you could think of it as scientific. Performing a deliberate test, and this is actually why I was doing it, because I was benchmarking, and my throughput went down, and I wanted to have a good benchmark. It's like, well, I don't want to have 20% off the table. I need to resolve it and figure out why.
I'm going to pause here.
What could it be? What else could it be? Rotational disks. We had a data center alarm. Maybe it's vibration.
Okay, I got to show you this. Yelling at JBuds. This is a video that he's like infamous for. Yeah, I'll do the same thing where I play it on both. Give me 1 second. I need to figure out the latency issue on my audio over HDMI, so I don't have to do this silly synchronization. Oh.
Hi, I'm Brendan. We're here in the Fishworks lab.
Sorry about
for
that.
Screaming. It's very loud in here with the air conditioning.
Sorry about that. I'm gonna lower the volume on that one. All right.
Some servers all around me. We just made an interesting discovery, and we thought we'd show you straight away. So over here I'm measuring disk I/O operations broken down by latency. I've also drilled down to disk I/O operations taking at least 520 milliseconds broken down by disk. This is using dtrace so I can do performance analysis of disks. I'm applying a write workload to 2 JBODs, which are over here. The lights are blinking on these JBODs because they're doing work. What I'm going to do is not recommended. This is not supported. Do not try this at home. Ah!
He yelled at the discs.
Not special effects, this is real. What we're looking at here is the effect of disk vibration. Vibration is a serious issue, and we can see the effect here that it's caused. So here, the latency for the disks that are under the workload has gone up. Here I can see which disks have now had I/O operations longer than 500 milliseconds, and I can find out that they belong to the JBODs I was just shouting at. So, amazing stuff. This has been made possible by analytics from Fishworks, which lets us look at things we've never seen before. Disk latency, high latency caused by vibration is a real issue. You've seen it. It does exist.
Just don't let Brendan shout at your discs.
That's right. Don't shout at your JBODs. They don't like it.
Yeah, it's mostly. I mean, that video is like 17 years old at this point. It's mostly for like like mechanical hard drives. Like if you yell at your NVMe SSDs, it's not gonna have an issue. But the vibration from yelling was enough to cause those read-write heads on the mechanical hard drives to have read-write errors and increase latency. Yeah, they're super sensitive. And one of the issues with they call it vibe or vibration. Like in a data center, you have all of these mechanical things, fans, and like hard drives, and just vibration in the data center. And it just like all that stuff. It's hard to control for that, you know. So it is interesting that that had such a pronounced effect. That's what he's talking about here. So his question was, why did write throughput drop by 20%? Hypothesis disk vibration by data center. Alarm. I guess there was an alarm going off in the data center, which happens a lot in data center. I used to work in a data center. The alarms go off all the freaking time. Prediction, any loud noise will reduce throughput. The test was yell at the JBODs and see it happen. So this is him using that method, I guess. Let me go ahead and start this back up.
I didn't have test equipment to reproduce noise, so I just used my voice. So, scientific method. Pros, good balance of theory and data. Generic methodology works for anything. Encourages thought and develops understanding. Cons, the hypothesis requires expertise, and it's time consuming. It's more suited for harder issues. It does take a while to get through all of this. Workload characterization method. So this one's great. And it's another methodology you can follow. It's looking at the input to the system, or the input to the target. We're not going to look at the resulting performance. We're just going to look at the input provided. So that could be who is causing the load? What's the process ID, user ID, IP address? Why is the load being called? What's the code path? What is the load? What's the IOPS, the throughput, the type, the read or write, synchronous or asynchronous, file system I/O? And how is the load changing over time? As an example, I blogged this one. We had a customer with a system log checker, which was much slower after the system upgrade. And so I like to begin with workload analysis fairly early on. And grep was on CPU for 8 minutes.
Why alarms?
And it was a small file. And so that's the who. So why was
basically, like, you don't want an outage to happen because of moisture, humidity, smoke. Sometimes capacitors will blow out, causing like a puff of smoke to go up into the air. Like all these things are all carefully monitored in a data center. The atmospheric consistency
highlight what is being asked of the
and there's
system.
systems in place to avoid any catastrophic damage to the data center. And so alarms are like are really trigger happy to get people in there to figure out what happened, you know.
And the best performance wins are from eliminating unnecessary work. So I'm trying to when I have time.
I might actually pause the video here and pick it up tomorrow because I'm getting kind of tired. But I'll leave you with a story about when I worked at a data center. The worst data center accident I've ever seen. It almost ended in like someone dying, but fortunately it didn't. But the data center had this fire suppression system in it that would flood the entire data center with this gas that basically would push all the oxygen out of the data center. So naturally you would think like that's not really great for human beings, and it isn't. Like if you're on the data center floor when that happens, you need to get the hell out of the data center. So what happened is someone was doing maintenance on a backup diesel generator, like switchover. So basically what happens is like when there's a power outage, you have all these backup power systems for the data center, but they take time to spin up. Like diesel generators cannot instantaneously start producing load for the data center, can't producing power for the data center. So you have a bank of batteries that will immediately start powering the data center for a short period of time while that diesel generator comes online. Well, there's a whole electrical infrastructure set up to shift the current from the grid to those batteries to the diesel generators, and that system was under maintenance. From what I understand, I didn't actually get a full post-mortem on what happened, but my understanding was that system was under maintenance, and someone dropped a wrench into this interconnect, and it basically arced like a lot of current and a lot of volts, a lot of amps, a lot of volts through this wrench connecting these two things. And of course it caused a major outage. It was also like huge, potential, risk to human life. But because that arc happened, basically the wrench evaporated and turned into smoke, and that smoke went into the air, and then that triggered the fire suppression system, which then flooded the data center with this gas that pushed all the oxygen out to keep any fires from affecting the equipment in the data center. So it was a massive incident for the data center. Fortunately, there was no loss of life or damage. No one was injured, and the only equipment damage was that power connection, the transfer connection thing. But I was there. I was on site when that happened, and it was kind of crazy. Yeah. So yeah, data centers are crazy. They're noisy. They're hazardous. Like anytime you enter a data center, you want to have noise protection. Usually they have like a dispenser of earplugs that you can put in, or a headset like this that's even more protective of your hearing, because it's so loud. Like you don't want to be in there for prolonged periods of time, or you'll just damage your hearing. Yeah, I mean the alarms that day were going off like for hours, and they evacuated the building. So I worked in an office building that was like one wall away from the data center floor, and they evacuated that entire building for, I think it was a good 5 hours. I think it was an entire day maybe. But yeah, it is interesting, like all the systems they have in place to protect equipment and ultimately to protect people's lives as well. Cool. All right, so I'm gonna hop off here because I'm getting kind of tired and it's past my time I'm supposed to be logging off. That could have been scary for weeks. Yeah. I mean, you could smell the smoke for a while for sure. I remember that. All right, I'm gonna hop off here. I'll pick up this talk maybe tomorrow morning, maybe tomorrow afternoon. I want to do more of this, like, watching talks with a little bit of a critical mind towards what's going on instead of just like mindlessly watching conference talks. This one was very heavy so far on methodology, and a lot of these methods, I mean, I'm not a performance engineer, so I'm not going to be like applying these directly, but some of them you apply just when you're debugging software. So the general methods that it'd be nice to kind of keep fresh in my mind when I encounter situations where I don't know what's going on, being able to figure out what's going on. Yeah, I think it'd be helpful. Cool. All right, I'm going to log off then, and I'll pick this back up tomorrow, and then I'll probably start on this book tomorrow then, which is all about BPF performance tools. And my main objective with it is just to learn how to instrument my own code and the code of the operating system to be able to figure out what the hell is going on. It's more for the purpose of understanding. And I think that's really the at root of debugging is understanding. You can't debug a problem that you don't understand. So my goal with this is to learn more about how systems operate. Cool. All right. Well, I'll be on tomorrow most of the day. I do have like a meeting in the afternoon that I have to attend, but yeah, I'll be on in the morning and most of the time in the afternoon tomorrow. Cool. Hopefully you got something out of this one. All right. Have a good one.